beautiful people. In this video, we will be graphing logarithms using reference points. Now, there's different ways of graphing logs. The way that our book does it, the way that we're going to be doing in class, we'll be using reference points. If you wish to view a different method, then definitely reach out and you and I can have a little chat. All right, let's go ahead and get started. So since we are using reference points, we're going to be needing our reference points formula. Now, I have a quick little sketch here that I'm going to do here in just a little bit. Well, let's jump down for our parent function versus our transformation. The reason we like using reference points is because they include transformations into the points. What happened to the parent function point when we have x, y, and z happening? So for our first reference point in our parent function, now notice for our parent function, we do have two unknowns. We have a b as a variable and we have an x. So b is our base is our original, that was a, but since we are graphing, we are calling it an x for a variable. So the first reference points that we're going to have is we're going to have 1, 0. Secondary reference point that we're going to have is b, 1. Now this is for the parent function. No transformations have happened yet. The asymptote, do not let this be confused with the asymptote from an exponential function. Again, exponential functions and logarithms, they're inverses, and logarithm is an exponent, so the position has shifted. The asymptote for a parent function is x equals 0. Now let's talk about our transformations. What happened? Well, just like when we originally were learning transformations, and I told you, you will need this throughout the entire school year and for the rest of your mathematical career, everything's the same. H is our horizontal, always think opposite. K is our vertical, up and down, shift. The A is our vertical stretch or compression. Nothing has changed. The B value is the base, or you can think of it as the base of the function. All right, let's talk about reference points one more time. This time including our transformations. The first reference point is going to be altered by adding h or minusing depending on what the h is. But you're going to add h to that value, comma, k. Secondary reference point gets changed to b plus h, comma, a plus k. And the asymptote, this is where don't let this confuse you with the original exponential asymptote, and that is our h value instead of our k. Now, inverses are logs and exponential functions. So the exponential function that we originally had for our asymptote of k, we now have asymptote of h. So don't let that confuse you. Let's go ahead and graph just a basic logarithmic function for our parent function. Again, this will change very slightly depending on your b value. So for example, and again, this is an example of a parent function, just so we have an idea of what it is. If you don't like f of x, just use y, and let's use log base 2 of x. Now, because a base of 1 doesn't really do anything, we can't really use that as a gauge of how our parents will behave. So let's do this. First point is 1, 0. Second point is b, 1. Our b value in this case is 2. And our asymptote is x equals 0. Now, one thing I am actually going to grab my red marker here. The asymptote, because we are doing the inverse of an exponential function, the asymptote is a vertical. So vertical, up and down asymptote, not horizontal. We're no longer doing a horizontal. Think inverses, think opposite. If we had a horizontal asymptote for our exponential function, we now have a vertical asymptote for our logarithmic function. Okay, let's go ahead and graph this. Let's graph our asymptote. Here's our asymptote at 0. And it's x equals 0 now instead of y. And our 2 points, 1, 0 and b, 1, in this case 2, 1, b, 0. And again, be careful not to cross or touch your asymptote. Be careful. So it does end up cutting off. So in this case, here's our asymptote, our curve. It's going to look something like this. We're going to get exponentially close to your asymptote here, but we're not actually touching. Let's go ahead and do a few examples using our reference points. Again, here they are. Write them down on a cheat sheet. I don't expect you to have these memorized, especially coming after an exponential unit. So write these down, make sure you have them, and know the difference between exponential and logarithmic reference points. All right, this comes directly from your book, so you could potentially have these questions in your textbook. They could be a little bit different, but it says graph each function, find the asymptote, tell how the graph is transformed from the graph of its parent function. So they're asking us a lot of things to do. We're going to use our reference points immediately. I'm just going to write them down here. So I have 1 plus h, comma k. I have b plus h, comma a plus k. Now these are for b values greater than 1. And then our asymptote is x equals h. It's no longer y, it's x now. All right, let's go ahead and graph this here. Our function, our transformed function, is a times my log base b of x minus h plus k. So k is now 4. That means we have a vertical shift of 4. Our b value is 2. Our a value technically is not there, but it's 1. And our h value, since there's nothing here next to x, that means our h value is 0. So basically what you're looking at, if we expand this just a little bit, we have 1 times our log base 2 of x minus 0 plus 4. Do you need to write that out like this? No, I just wanted to show you where those values came from. Let's do our 2 reference points and our asymptote. So our asymptote is going to be x equals h. So what is our h value? Our h value is 0, so that is my asymptote. And again, this is my vertical asymptote. Our first reference point is 1 plus h, which is 0, comma k, which is 4. So my first reference point is 1, comma 4. My secondary reference point is b plus h, comma, a plus k. So in this case, I have 2 plus 0, comma, 1 plus k. K is 4. So my secondary reference point is 2, comma, 5. So let's identify where our vertical asymptote is. In this case, it is at 0, always dotted line. So we know that our parent function is going to look something like this. It's going to look something like that. And I said parent function. So we know our parent function looks like this. So we know our transformed is going to look something like that as well. So let's do 2 points, 1 and 4. So this is 2, 4. 2 and 5, something like this. And I'm going to just use a different color to sketch this out. That goes off to infinity beyond. It does curve a little bit as it increases. Something they didn't ask us, but let's talk about your end behavior. So as x approaches infinity, what happens to our y value? So as x gets really, really big, what happens to our y value? Well, it gets really, really close right here to infinity as well. But notice x cannot get exponentially small. Like it can't happen. What we do get to is as x approaches, what does x approach? X approaches 0 as y goes to negative infinity. You can't switch these up. Sometimes you're going to see it written as y approaches infinity, x approaches infinity, and then y approaches negative infinity, x approaches 0. You'll see that sometimes flipped around. Let's do example number 2. And I'm going to just jump in here with my reference points. Let's identify our transformations. I have a vertical stretch of 3 as my a value. I have a base of 4. I have my h value, always do opposite of negative 6. That means I'm shifting 6 jumps to the left. And for my k value, I don't have any shift up or down, so my k is 0. For my reference points, I have 1 plus h, so 1 plus negative 6, comma k, k is 0. For my secondary reference point, I have b, which is 4, plus h, which is a minus 6, comma a, which is 3, plus k, which is 0. Again, I'm having my cheat sheet right here. And then, so let's go ahead and solve this real quick. So my first reference point is at negative 5, comma 0. My secondary reference point is at negative 2, comma 3. And my vertical asymptote is at h, which is negative 6. So x equals negative 6 is my vertical asymptote. So let's find this negative 6. Negative 6 is right here. Make sure you do a vertical asymptote for logarithms. First point is negative 5 and 0. Secondary point is negative 2 and 3. Negative 2 and 1, 3, like this. Again, it's going to have a curve, just like an exponential curve had a curve. Logarithmic is also a curve. And again, just let's do our end behaviors here. So as y approaches infinity, so as y gets super duper big, what happens to our x values? Our x values also get super duper big. But as y gets smaller, so as we go down, what happens? Well, as we go down, as we approach negative infinity with our y values, we're going to get extremely close to negative 6. However, we're not going to touch negative 6. Let's do one more. I'm going to skip this one here. I'm going to do one with a natural log. Don't let that scare you. Natural log is just a log with a base e. So I'm actually going to rewrite this as a log with a base e. So 3, let's do y. Y equals 3 plus ln x. Again, natural log of x. So I'm going to do y equals 3 plus log base e of x. And I'm just going to move that 3 over just because my OCD is kicking in and I prefer my k values to be on the other side. You can put that x in parentheses if you wish, so you don't think that 3 is your h value, which is not. All right, nothing really changes after that. So we have our first point at 1. Oh, let's identify our points first. So let's do a is 1. Nothing in front of log. Here, being multiplied, keyword multiplied. That means a is 1. H, again, is inside next to x, which is 0. What do we have? B, our base is e. And then what do we have after that? Our k value is 3. Our asymptote, our vertical asymptote, is our h value. In this case, it is 0. Use a cheat sheet so you don't get that confused with the other lesson that we had. And then let's use our reference point. So I'm going to write our reference point here since I'm running out of room over there. Reference point 1 is 1 plus h is 0. And k is 3. Secondary reference point is b, which is our e value. Again, e is irrational. It continues forever and ever and ever. It is not a variable. And we have b plus h is 0, comma, a, which is 1, plus k, which is 3. So we have 1, comma, 3 as our first reference point. Second reference point is e, comma, 4. Now, some of you made a hiccup on your previous test, assuming something is an exponential function with a base of e when they didn't tell you that. So any point that has e in it, we know that it has a base of e. So here are 2 points. I don't know what e is, exactly, because there is no exact value of e, but I do know it's 2.72-ish, and then 4. So let's use our asymptote, vertical asymptote of 0. Then we have first point is 1, comma 3, which is about here-ish. Second point we have is about 2.72. So 2.72 is about here-ish, almost at 3, not really, and then 4, which is here. And we're going to do a curve downward towards our asymptote and a curve outward for the other side. All right, let's do our end behavior. So as y gets super duper big, you should be noticing a pattern here. X gets super duper big. And then as y gets super duper small to infinity, what happens? Well, we approach our asymptote, our vertical asymptote towards 0. The function, let's do this one here real quick. The function f of x equals log of x plus 1 is reflected across the x-axis and translated 4 units down. So how would we write that equation? Well, think back. If it's outside the bubble, if it's outside the function, that means it is vertical up, down. If you are multiplying, then you have a stretch or a compression. If you are inside the bubble, if you're inside the function, then you are horizontal and you're always doing the opposite. So in this case, here's our function, and we want to reflect it across the x-axis. When you're reflecting across the x-axis, you're actually changing the vertical side. So we're going to be outside of the bubble. So I have log. That is now negative. You can do -1 or you can just put negative. Again, there's no base. That means we have a base of 10. X plus 1 is inside the bubble. And translated down 4 units, down means we're changing the y, means outside of the bubble, and we're going down 4 units. You can set that equal to y, or you can set it equal to f of x. Let's do one more time. The function is compressed vertically by a factor of 2/5 and translated up 11 units. Again, vertical means outside of the bubble. So our factor is 2/5. We have 2/5 times our log base 8 of x minus 3. And we have a translated up, again, vertical is up, 11 units. So we're going to add that by 11 and set it equal to y, or you can do that. I'm going to skip this number 7 as we're going to do a separate video for word problems. I hope you enjoyed this video, and I will see you in my next one. Bye!